Okay, so what we are going to do today is just to finish off the descriptive statistic. Okay, so in the past lectures, we have run through how to tell the characteristic of the data set, which is the main point in descriptive statistic. Okay, this is just a reminder of what we have done. We could use central tendency or the average values to explain or measure the features of the data, which is a characteristic of the data. Okay, we can also tell how dispersed the data is. We can tell how asymmetry the data is, and also the last lecture we talk about how we explain the relationship or the correlation of the data sets. Okay, and just to note that in the three first measure of the data involve each set of the data, which is the univariate population, the data population. But once you get into more than one set of data, you can actually find whether the data has any relationship, which last time we talked about correlation. Okay, to show if the two set of data correlate to each other. Okay, and I have introduced to you that correlation just tells you how much the two data set is to tell how much the data set is correlated, and for the regression it is to tell the cause and the effect of the relationship. Okay, so basically, yes, last time we talked about two type of the correlation, okay, which is Spearman coefficient of correlation, which is a ranking. Okay, you have to put data into ranking first before you actually do calculation and to get a values to say how much they are related to each other. Okay, and Pearson coefficient is the linear relationship between the two variables, and just to tell them how they are related. No need to rank. Okay, and I did mention a little bit that the Pearson correlation is very close to the R-square values. Okay, which is what we are familiar with when we plotting the graph and then doing the R-square values. And we have the example. Okay, now today we are going to talk about the regression. Okay, last time is a correlation to tell, it's telling how the data are correlated to each other, and now it is a regression. Okay, regression tells the relationship between cause and effect. Okay, dependent variable and independent variable, so to say. So very likely when we have regression, we will have like an equation to explain the dependent and independent relationship. So regression is a study of a statistical relationship between two quantitative variables. Okay, and in the real world, the relationship is not perfect. Okay, so even though you have like a straight line trend, every point will not be sort of like straight. Okay, so it has some variation. So the exact relationship is not normally happens. Okay, but there do some there are some exact relationship, which is for example, the formula, like the exact formula, like changing Celsius to Fahrenheit, it has some form of equation and it is exact. Okay, so that is the exact relationship. But most of the time, especially in our in the experiments, okay, the relationship is not perfect. Okay. So when we talk about simple regression, I'm talking about simple regression, okay? We are not doing sort of like multiple or more complex regression. When we talk about simple regression, we are talking linear relationship, okay? And everybody is familiar with linear relationship, right? So it's more or less like y equal to mx plus c. Okay, so that is the linear equation. So simple regression is a linear relationship, and it has two types of variable. Okay, it's independent variable is what we call the predictor, and dependent variable is what we call the response in statistic. So independent variable is something that if you are related that to the experiment that you do, independent variable is the variable that you have the fixed values, and independent variable is the response that depends on the value of the predictor. For more example, it's like when you are doing your experiment, you want to vary temperature and see how the cell is growing by measuring the optical density of the cell. So the predictor would be temperature, right? So it is independent variable. So you pick it that at what temperature you want to do your experiment. And the response is the cell optical density. So it will change with the temperature. So at temperature of 20 degrees Celsius, you get this value of OD. Changing it to 30 degrees Celsius, you get a different value of OD. So the optical density is the response. And like I told you earlier, linear relationship, the equation is y equal to mx plus c. So that's what we all know, right? So we all know that it is y equal to mx plus c, which is a simple equation that explains the straight line. Okay, so you have y, which would be your response. You have x, and then it's a linear with slope values is m. Okay, so it depends on your x that what your y would become. So that is a simple regression. Okay, so you can use the symbol like mx plus c, or you can have like b1, b2, or whatever it is. So in this case, b1 is m and b0 is c, and you know that m is a slope and c is the y-intercept. Okay, so that means that when your x is 0, what is the value of y would be? So that is the y-intercept there. Okay, so that is the simple linear relationship or a simple regression. Okay. Okay, so to say, in real life, when you have a linear regression, when you want to see linear regression, you have sets of data, but like the data set will not go like straight. Okay, so you don't have something that, okay, this data point is here, this data point is here, this data point is here, and that data point is there, and wow, it's like 100% linear. Okay, so every point is on the linear line. In real life, it's not going to be something like that, especially when you do experiment. So in doing experiment, you are likely to get different points, okay? But it has a trend, like for this example, it has a trend of being a straight line. So you can assume that X and Y has a linear relationship, and you say that, okay, since it has linear relationship, so I think that I could fit an equation which is a linear equation to this set of data. So that is a simple regression. Okay, at the end for regression, what you have is you are having an equation. Like in this case, this is the equation. Okay, you know that this equation, it has a y-intercept of 5, y-intercept of 5. So that means that when x is 0, y is 5. So likely that b0 is 5 in this case. Okay, and the slope is what you can actually calculate. Okay, and that would be the slope. Okay, and the expression of each individual values, like each blue dots, would be like x, the number of data. So like if it's x1 y1, so okay, let me give you example. For in this case, it would probably be the first value of your experiment. So it could be this one would be the set of experiments. So this one could be your x1 y1. Okay, that could be your x2 y2. So each data has its own values. Okay, so I'm having this I'm having this expression because when you have the expression in this equation, you could replace the I with the y values. Like for in this case, so if you have y1 equal to y1, if it is like 5 plus something x1, so if your x1 is 10, and this is the equation of the red line, right? Your y1 would be something here which is about 7. So that sort of thing. So if you have y2 at 20, then x2 at 20, your y2 will be somewhere around 8. So that's how that's how it goes. Okay, the point is that, for example, right, if in your experiment, and the value that you get from your experiment and the values that you get after you are doing regression would be different. Okay, so for example, take the example of this one. Okay, take the example of this data. I'm using different. Take the example of this data. Okay, take the example of this data. This data belong to x of the x values here. Let me say roughly 29. Okay, roughly 29. In actual experiment, when your x is 29, your y is about 5. Okay, so other dot of the blue dots will have different x and different y. The point is that after you decide that you will make a regression, the equation of the regression that would predict how the set of data will relate. Okay, at your x of 29 on the regression line, your x is no longer 5. Your x would be like 9. So that's why you have the value that you get from the experiment and values that you get from the regression line. Okay, I'm not sure how many of you has attended this morning's seminar, they have experimental values and predicted values, right? So in one of your friends that present in the seminar, she's doing experiment and then she fits that experiment with some equation. So she has the experimental values and predicted values, which comes from the equation. So that's how it is. It is like this. Okay. So the experiment give you at 29, the experiment gives you 5. But when you make a regression, okay, when you make a regression of the whole set of data, that x of 25 will give you 9, which is on the regression line. Okay, so that's how when we are talking that, okay, we are doing modeling and then we get when you do modeling and then you get the model equation and then you have experimental value and predicted value. That is that is the idea. Okay, that is the idea of regression. Okay, just that in your friend's example, the regression is not a simple linear regression like this. That's all. All right, so that is to give you some idea about regression. Okay, and let's go next. Still on the regression stuff. Okay, look at this set of experimental data. Okay, each point, I mean the circle point is from the experiment. Okay, is from the measure, the actual thing that happened. So this example is the relationship, okay, between height and weight of how many people we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, of 10 people. Okay, height and weight of 10 people. Okay, and when we plot the relationship of these 10 people, you see that, okay, it probably have a straight line, a linear relationship. And then you decided that, okay, we are fitting a linear curve into that. My question to this one is that, what color do you think is the best fitting line? I mean, what of the two lines, like whether red or green, that appears to your eyes as best fitting? Please type down your answer. I mean, looking at that, just looking at alone, don't think about other thing else. What do you think is the best fitting line? Red or green? Just guess, type. And just type in, I guess it's red, I guess it's green. Okay. Okay, epic thing is green, right? Okay. What about other people? เราคิดว่าสีไหนที่ฟิตดีกว่าค่ะ Okay, you think it's red, you think it's red. Okay, what else? Some people think red. The rest of the class, what do you think? We have 1 green and 3 red right now. We have 1 green and 3 red right now. I just want to see how people think. Okay, we have green. Okay, we have red. Okay, so some people think green, some people think red. The point is, how do we know which line fits better? How do we know which lines fit better? Okay, if this is in Excel, okay, you probably just put on the function trend line, right? And trend line will give you the best fit, and it will give you like R-square. And then you say, okay, that is the best line. Okay, I'm not going to say which one is good first, because it's if it's in Excel, it's just easy. Okay, it's just easy. The point is that what I want you to think is, when fitting a curve, when fitting the data with different equation, how would we determine what equation is better? Whether it's the equation with the red equation or with the green equation, which equation is better? Linear curve is easy. You just use Excel and, just do it. But have you ever thought that how does Excel tells you this is the best fit line, this is the best fitting line to the data that you have? Okay. And frankly, in Excel, okay, in Excel, you have so many choice, right? You can choose to fit your data using linear. You can choose to fit your data with power. You can choose to fit your data with exponential equation. So you have so many choice. Okay, just that if you see it as a straight line, okay, maybe it's linear. Okay, but it also fit other equation as well, right? So there must be something that tells you that the equation that you chose is the best equation which fits your data. Okay. That comes to the concept of what's called the best fitting line. Okay. The concept of what you should use to tell which equation would give you a best fitting line. Okay. Before we go to that, you need to understand the word residual errors. Residual errors. See, I haven't actually talked about R-square or anything yet, because you might have thought, okay, the best fitting line is the one that gives you like the best R-square. Okay, I'll come to that, to your idea of what is the good R-square for fitting in your opinion a little bit later. Okay. So the concept of finding the best equation to fit your experimental data, okay, start off with, you need to understand what is residual errors. Okay, residual errors is how much the predicted values is differ, or how much different between your predicted values and experimental values. Okay, the symbol is this one. Okay, just the residual errors is the difference between experimental data and the fitted data. To simply go back, okay, go back to this slide. You see the symbol here, the one with little hat on top. The one with little hat on top. That is normally referred to as the predicted data, which is the data or the values that the predicted values. It is the values that you get from the equation. Okay. So let's see. I'll take this example again. This example again, this point. Okay. So this point, okay, this point at about 29, your experiment give you the value of about 5.5. Okay, so to say. So this 5.5 will be your yi. Okay. But the predicting values from the equation is actually about 9. So your yi hat is 9. And it is the calculated values using this equation. Okay, so your residual errors is simply 5.5 minus 9, which is 3 minus 3.5. Okay, so that is residual error. So it is the errors that happen is the difference between what's predicted using the equation that you think it fit and between and the values that you get from the experiment. So the difference here, okay, is the difference here is about 3.5 minus 3.5, the difference between these two lines. Okay, so that is the residual errors. Okay, so you probably get some idea now. Some of you might get some idea now that if we have that so many experimental data, for each of the point we'll have its own residual errors, right? Like for this one, the residual errors, this is from the experiment. That one is from predicting from the equation. So the difference there is about 3. So that is another residual errors. So the first concept here is that you probably get some maybe some people some of you get the idea now that, oh, okay, so the line that best fit the experimental data must have a very small errors, right? Okay, like for in this for this case, the errors for the green, the residual errors for the green line would be the difference here, right? From that one, this one is on spot, that one is on spot, that one is that much different, that one is small different, that one is that different, the different, this one is almost on spot, and that one is different. Okay, while the red line, the different the red line, the difference is that much, that much, that much, that one different from the line, that one different from the line, and that one is the different from the line. So the two lines produce for the two lines, and for each of the data, they produce different errors. Okay, just to show you, taking the example of the last point, okay, that point. Okay, so that point, the red, the difference in red to the errors from the red line is that much, but the errors from that line, from the green line, okay, is that much. Okay, so that is residual errors. Okay, so with the concept of residual errors, okay, it comes to what makes that line or that equation fits the experiment values better or best fitting line. Okay, the concept here is called the least square criteria. Okay, the least square criteria. What we are trying to do in the least square criteria is this. Okay, you see that this is the residual errors, right? This is that equation. Okay, the least square criteria say that for each of the data point, you will get each residual errors, right? When you square the residual errors and then plus all the residual errors together, whichever equation that give you the lowest Q, minimize Q values, which one that give the minimum Q, least Q, is a better fitted one. Okay, so that goes into this. If we looked at if we looked at this graph, so that means that to see which one is better, okay, you have to find the residual, you have to find all the residue of the data and the red line, right? And also the residue of the data to the green line, okay? And according to the formula, you square each of them and sum them up, okay? So that means that for the we have 10 data set here, right? So for the red line, for the residue of each one to the red line, each of them you square and then you add, okay? And then you get a values which is Q, okay, according to that one. And also you do the same thing, but using the equation for Y, for the green line, and then you get the values, okay? So which one goes into the cost, like the Q values to be lower, is the better fitting line, okay? Why do we have to square? Because these values, okay, could be positive or negative. Okay, if your yi is smaller than predicted, you get negative, and if you sum the negative and positive, you wouldn't get like a good estimation of Q based on this concept. So you have to square them to eliminate the negative effect, and then you just plus them together. Okay. Right. This is the concept. Okay, this is the concept. The point is that with this concept, okay, if you have a tool or a program to calculate the least square, like in Excel, you can do like solver and things like that. Then you can tell, you can actually find the best fitted mode, the best fitted line, or the best equation that could fit your experimental data. Okay, so that is the concept. Okay, find the best fitting line doesn't mean that you get the best R-square, because best R-square is very difficult to tell which one is which. Okay, so the concept of least square criteria is used to find the best fitting line. And it is very useful in modeling and things like that as well. If you enroll in next semester laboratory in biochemical engineering, we will apply this concept in the modeling and simulation lab. Okay, now, since I have introduced to you the concept of the best fitting line, so at least you get some idea that R-square is not the final answer in all the case. Okay. Now looking at the R-square itself, okay, the R-square itself tell how close the data are to the fitted line. Okay, it doesn't tell that the sum of the residual error square is the least, but it's just an indication of how close the data are to the fitted regression line. Okay, and when I say that R-square may not tell you exactly or directly that the line is the best fit, because R-square values is actually comes from the calculations. Okay, and this is the formula that used to calculate R-square. Okay, so R-square is calculated from the regression sum of square. Okay, I'll explain a little bit later. I just want to show you that it comes from the equation. Okay, so R square is the ratio between regression residual and total sum of square. Regression sum of square and total sum of square. See that up there. Okay, and it could translate it into 1 minus sum of square of errors divided by sum of square of total. So that's how the formula goes. Okay, and you can play around between these two formula. Once you understand each of the sum of square, I want you to notice that it is called sum of square because you square then sum. Okay, you square then you sum them up. Okay, you square and then you sum them up. Look at each of the type of the sum of square which is used in R-square calculations. Okay, the first one is regression sum of square. It is the difference between predicted values and the average values. Okay, and everybody knows average, right? Like for that graph with the 10 data, you average arithmetic average of the 10 data is your y bar. Okay, so whenever you see a letters with the bar on top in a formula, most of the time it is the average values. Okay, so it's average values. Y with a little hat, it predicted values from equation. That's what we covered earlier. And the Y without hat or bar is the experimental values. So this formula, you just follow this formula and then calculate these values. Okay, and that how you get values for calculating your R square. So looking at this formula, your R square, okay, your R square could be the maximum of 1 and the minimum of 0. Okay, looking at this equation alone, if SSE and SST is 0, that's when you get R square of 1. Looking at SSE, which is error sum of square, right? The only way that this value is 0 is when SSE is 0, right? 0 over something is always 0. So when it is 0, that means that each values from your experiment is exactly on the line of the equation that is created. So that's when these two values are equal. Then at every point, then your SSE is 0. Okay, so see, if your SSE and SST is equal, which is 1, that means that your R square is 0. So that's how it goes. Okay. Now let's see first before we go into the next slide. Okay, so I am introduced this R square, so we could go on to the next slide. Okay, so everybody knows that R square equal to 1 is the best. So the data point fit perfectly with the regression line. The regression line is the line that you produce from any equation. Okay, and R square equal to 0. The only thing that that could happen is regression line is horizontal. Okay. Now, may I ask, you can type in your answer. In your opinion, what is the value of the R square that you think gives you the good fit? I'm asking this question because a lot of people using R square solely to see whether it's a good fit. can each of you type what is the R-square values that you like? I mean, is good for you for the best fit? Yeah. You know that, I mean, I'm asking this question because I want you to think, because you are going to see R-square all the time, and every one of you knows that it's quite impossible to get R-square equal to 1. But if you want the R-square to be some values, what do you think is the R-square that is acceptable to you? 0.99. Okay, so that means that if you don't get 0.99, you are not happy with your data, right? Okay, some of you say 0.95 and above. Okay, so more than 0.95. What else? Who else? I just want to see your idea, okay? There's no mark in it. I want to see your idea. If I know what you are thinking, maybe I could explain a little bit better or get you to see something easier. พวกเราคิดว่าค่า R square อะไรที่เราเห็นแล้วเราบอกเฮ้ยมันฟิตโอเคแหละอะไรอย่างเงี้ยนะคะเพราะบางทีอาจารย์ก็เห็นแบบเราเขียนในเปเปอร์ในอะไรพวกเนี้ย R square 0.9 เรายังแฮปปี้เลยอ่ะอาจารย์ก็เลยอยากจะรู้ว่าในความคิดของเราเนี่ย R square ขนาดไหนเราถึงบอกว่า curve fit โอเคOkay, I have some time for you to think a bit, but I really encourage you to type down something so I know what you are thinking, okay? So no one has any input or don't wait for the right answer because what I'm asking is I'm asking your opinion อาจารย์ถามแค่ความเห็นเราค่ะ Okay, some people say more than 0.98 is acceptable. All right, okay, if you don't have any idea, okay, we just go on, okay? Okay. I just want your opinion. Whether R square of 0.985 good or bad. Please type in the chat. ค่า R square 0.985 เนี่ย ถ้าเราแบบเห็นแค่ค่า R square เราคิดว่าค่า R square 0.985 เนี่ยดีไหมคะ Just type in or good or not good พิมพ์มาแค่ว่า good หรือไม่ good อะค่ะยังไม่ต้องดูรูปเอาแค่ค่า R square นี้ก่อน Okay. 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 Some of you think that is good, 0.985. I remember in seminar, okay, think about your own seminar. If you are doing modeling and the paper say that R square of 0.96 is pretty good, okay? So think about that, okay? Now, let me ask you about the pictures. Okay, the pictures. Do you think the graph fit well with the experimental data? The experimental data is in dots, okay? And the equation is here, and it produces the line, the blue line. Do you think the blue line fit well with the data? Yes or no? All right, so you think it's a no, right? Okay. Now, okay, I'm not going to ask you why do you think it's no. I maybe just tell you straight, because the point is that maybe you have some bias about the R-square values, okay? Because what I see most of the time when you start doing the experiment, especially if any one of you are going to do things with response surface methodology, you are likely to get the R-square of about 0.6, 0.96 and things like that, and you think still that it is good. But anyway, this equation, okay, this line fitting curve, the curve that fit the data, it looks very close. Basically, you probably wouldn't get better than this if you are using this type of equation. The point is that the R-square here, okay, 0.985 is a pretty high, really, in fitting the curve. It's rarely that you get 0.99, okay, in your R-square when you are doing experiment and fitting the curve anyway. But one thing that the R-square cannot give you is the R-square cannot tell if the prediction are biased. That means that even though you seem to get like high R-square, maybe you can see that, hey, it fits okay in this region, it doesn't fit okay in that region, and it doesn't fit okay with that region. It seems like the blue line is overestimated in that region and in this region. So one thing, if you are doing curve fitting, okay, what you should always do is doing the residual plot. Okay, a good residual plot that should not have the trend. Okay, residual plot shouldn't have the trend. Okay, this one is having trend. Residual means the value from the experiment minus the value from the experiment minus the value you get from the graph, from the equation. And if it has a trend like this, going down and then going up, or maybe going like across like that, it's not good. That means that even though your R-square is 0.99, okay, it's still not good, because the good residual means that it should run along the horizontal line of 0 here. Okay, it should spread out and not having a thing like that. So frankly, most of the students, okay, will think that 0.98 is good. Somehow it's good to some point. Okay, I bet you don't get 0.99 even when you are doing your standard curve. Okay. Okay, so think about that. Okay, think about that. You get 0.99, that's good, very good for standard curve. Okay, but with the modeling is difficult to get 0.99. Okay, this is one thing that I want to tell you, that R-square, even though it's like 0.98, it's it doesn't tell you really that it's a good curve fitting, especially if it's not linear. Okay, that's why going back to simple regression, okay, the R-square would work well with a simple regression or with a straight line. It does not work well with the other type of equation. It could tell you something, but it wouldn't explain well with other type of equation because it can have like a pattern residual plot. Okay, you wouldn't get this if you are fitting a straight line. Okay, because fitting a straight line, of course, it balances between like the overestimation and underestimation because it's a straight line. Okay, you will get a pretty spread out residual across the values here. Okay, so be careful if you are going to judge something with R-square values. Okay. Now, I want to talk a little bit. Okay. I want to talk a little bit about a multiple regression. Okay. Whenever you see the equation like this, you see that it is still in the form of a simple regression. Okay. If you see the equation like this, it still be in the form of multiple regression, but it's in more than one plane. Okay. So you can still use the same principle of linear regression for the multiple regression, but in linear form like this. When I say linear, because nothing here has a square, nothing here has a log, nothing here has a power, like the equation is simply linear, okay, linear form, but has more than one predictor. So that's how it is, okay, and if it is the case, you can use a principle for the simple linear regression to explain the relationship of the data. Okay, so up to this point, one thing I want to stress is that if you are going to use R-square, be careful. Okay, you are using R-square, be careful, because R-square will only work well with a linear regression. If you start not having a linear regression, you might get, even though you get a pretty high R-square, you might, it will probably not fit well because it probably have some bias toward this part and that part. Okay, just to check whether it is okay, you have to do a residual plot. That's how it goes. Okay, now I'm having these values of adjusted R-square added to the lecture because some of you might have to come across this term when you actually doing a research on like predicting the best values or doing the response surface methodology. Okay. Let me ask you a little bit here, because since some of you has been experiencing the research for some times now, I just want to ask, have you ever Okay. Have you ever come across the word RSM? Response surface methodology. If you have heard or if you have seen in seminar, just type yes. Or if you are not, please type no, because this one will come up all the time. Or if your thesis will have to deal with response surface methodology. Okay, Epic said yes. Or something like CCD, box, Benken, maybe. Yes, yes, yes. Okay. Yes. Okay. Wait, I think most of you have come across this. Yes. Okay. Okay. The point is that so if that is the case, you might have come across the word adjusted R-square. Correct? So from now, just let me know if you have seen the word adjusted R-square or this R-square ADJ here. Have you seen it somehow? In the ANOVA table. Yes. Okay, for other people, I would guess that you probably know, okay? But you all have seen the response surface methodology. The point is, if you are dealing with response surface methodology, trying to find the optimal using the research design, whether it's CCD or box Benken or anything that will give you like a model equation and predicting the value from the model equation. Apart from R-square, you would probably see the word adjusted R-square, and it is different. Okay, the values that you see is different. Some of the research, some of the data, you get a very close adjusted R-square and R-square, but some paper, the adjusted R-square is different from R-square. Okay, and yeah, what I put, the reason I put this adjusted R-square in, because I know a lot of you will have to come across, especially if your research is on fermentation or any type of thing that you have to do some experimental design, doing experimental run and using design expert program. You get the adjusted R-square, okay? So adjusted R-square is the modified version of R-square that adjusted for the predictor or the X values, okay? The predictor is the independent variable, okay, that are not significant in regression model. Okay, so the R-square, you have R-square whenever you have to have like a model. The model means the equation, okay? So y equal to mx plus c, that is the equation, that is the model, okay? So adjusted R-square is always smaller than R-square, okay? So if you have R-square of 0.99, your adjusted R-square might be 0.96 depending on your regression model. And adjusting R-square can be negative. If R-square is close to 0, that means that there's no relation at all, okay? Normally we don't see that, okay? So because the only way that R-square is close to 0 is when the regression line is horizontal, okay? You have horizontal, your M is 0. It happens sometimes in in um, in response surface methodology as well. If your response is very low throughout your surface, the predicting surface. Okay, so when we are talking about model or modeling or equation, okay, since it is a mathematical expression, so the more variable you put in, the better is the fit to the experimental data. Okay, but it doesn't mean, so the more data you get, a better fit you get. That's how it goes. Okay, and the more terms you get into the equation, the better the fitting would be. But somehow, sometimes the predictor that you put into the equation is not significant to your experiment. So R-square the adjusted R-square will indicate whether the predictor or the variables that you put into the equation will help improving the model. Okay, so if you have a low R-square adjusted, okay, it wouldn't help predicting the model. Okay, so the closer the adjusted R-square to the R-square is the best. That's how it goes. Okay, and it has some formula. Okay, it has some formula here. You see that the formula itself, okay, the formula itself is actually have the term, the extra term here, which is n, which is the total sample size. Okay, it is n here, sorry. This is small n, this is big N, but this is the same n. Sorry, that's my mistake down there. The P is the number of predictors. So how many X do you have in there? Okay, so simple linear regression, you have only one X, Y equal to MX plus C. But if you have like a linear correlation, but have many predictors, you probably have X1, X2, and X3. So you have 3 predictors, that sort of thing. So if this term is 1, right? If this term is 1, R-square adjusted would be equal to R-square. Okay, so that's why I said that R-square adjusted could never be equal to R-square, and it's always be smaller because of this term here. Okay, so basically adjusted R-square will actually tells you, okay, because the more predictor you have here, so that means that your model or your equation is more complex because you have so many terms added together. So the more complex your equation to predict your experimental data is, the lower the adjusted R-square as compared to the R-square. So that's how it goes. Okay, so at least you have come across this adjusted R-square, that it is different from R-square, and it tells you whether your equation contains too many predictors or it just have enough predictors, because the more predictors you have or the more terms you have in your equation, of course, the better the prediction of the model to the experimental data will be. Okay, so that's how it is. Okay, so to sum up the R-square, so R-square is valid only with linear regression. If you have power, or you have log, or you have not linear regression like quadratic or cubic or two-factor interaction type of equation, the R-square will not actually tells you everything. It doesn't actually tells you that it fits good or bad. Okay. It's the best to do the residual things as well. Okay, because if you go back, okay, if you have time and then go back and see the definition in calculating R-square, the linear model will tells you this, which is the case where R-square is working. But for the nonlinear model, okay, the R-square cannot be, I mean, that equation to calculate to tell the R-square will not be the same. So basically for linear model, sum of the square of the total equals to sum of the square of the regression plus sum of square of errors. But in nonlinear model, these two sides of the equation is not equal. So that means that the R-square doesn't actually apply to the nonlinear model. Okay, and yeah, I know that this is probably a little bit too deep for those who are not going to use it, but I just want you to be aware about the R-square and about the curve fitting. Okay, that the R-square is not everything, is not telling the relationship or the good or bad relationship except for the linear regression, okay, the simple linear regression. And if you want more information about the linear and nonlinear relationship, what are they and how they are different, you can go to the link that I show you here. Okay, so that is all about descriptive statistic. Okay, the last characteristic about the relationship of the two data set, okay, is probably the it contains a lot of things, and it crossed to the modeling as well, because it has the regression. It includes the topic of the regression, which is the regression, which is the cause and effect relationship. So it's a prediction of y values from x values. So because it's measure the relationship, that means that it has to include the regression as well. All right. Actually, that's what I want to cover for today, because next time we are seeing each other, we are going to talk about the inferential statistic. Okay, so inferential statistic is the next two lecture, and the last lecture I will show you. I'll find an example in the research paper for you to see how statistics involved in the research in biotechnology. All right, right now I'm taking any question regarding the descriptive statistic, starting from the first lecture up until today. And you can, if you want me to explain again on something, you can ask, and you can ask in Thai. I'll try to answer in both languages, like both Thai and English. Okay. Maybe for now we could have like a little break, so you can go to bathroom or taking a drink, or maybe you could think of what you want to ask me right now. Okay. Okay, let's see. I'll come back in 5 minutes, and then I'll take any question. Okay. Anyone wants to ask any question or anything that actually you come across in your paper, in your thesis that have some relation to what I talked about in the lecture? No one? Okay. If in that case, I want to talk a little bit more about the adjusted R-square, just in case some of you come across it. So, okay, you have to think about that. In this sort of regression, okay, we're not talking correlation, okay, we're talking regression, the cause and the effect. In regression, you tend to predict something from, you want to predict y from the x, right? That is the simplest form, okay? So that's what represent the linear relationship. And since the linear relationship is the most simplest form of equation you can use in predicting something. So linear relationship, you wouldn't have the R-square adjusted, okay? But once you get more term into that relationship, okay, that extra term is what introduced the R-square adjusted. Okay. So when you are doing like using design expert, okay, if you are using design expert, what you really want to do is that you want to get the program to tell you what experiment you do, and then you let the program calculate the equation that you would use to predict the optimal condition for your case, okay? And in doing so, if you have come across the use of the program itself, you have to tell the program what equation you want the program to fit your data, okay? Whether it's a simple regression, whether it's a two-factor interaction or cubic or polynomial of some sort, okay? So that is when the program will not only they calculate R-square, they will also calculate adjusted R-square based on the equation that you tell it to calculate things for you. Okay. The point is that it also has this type of R-square to tell you whether your equation is too complex, is too much thing in there. Okay, so most of the time, what I suggest in this case is that you're looking at R-square and adjusted R-square together. So even though your R-square, for example, if you are doing response surface methodology and your R-square is not so high, don't freak out with it, okay? Do not be scared, because R-square, like I told you, R-square by definition, it is the calculation, okay? It is this calculation, and this calculation is based on this formulation, and that only works with a simple regression line, okay? But you can use that R-square to calculate that formula to calculate the R-square, but the R-square itself, in the case of other model, which is not a simple linear model, will not tell you that much, okay? But what it can do, because linear and non-linear based on this the definition here. So that's why R-square we were in linear model based on that equation to formula to calculate R-square. The point is, in other type of regression, if you give a more complex equation, like your equation is very long and having so many things like x1 plus something x1, something plus x2 plus x3 plus x1, x2, x2, x3, x1 R square, blah, 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 blah. Okay, so you have so many terms. Okay, your R square will be improved with more terms added into the equation. Okay, the point is that adjusted R square can be used to tell whether each of the terms that you added in would actually help improving the fitting of the curve or not. So basically, when you start with doing modeling or finding the equations that is to fit your data, you will have the initial set of R square and adjusted R square. Okay, and the point is that if you want to drop some to make your equation less complex, because sometimes, okay, see when maybe you see more of this in the example. When you're doing ANOVA, it tells you which term is significant and which term is not significant, right? And if you want to drop some term out from the equation that is not significant, and if it is not changing the adjusted R square or only change adjusted R square for a little bit, you know that that term is not necessarily in the equation. So that's how you make use of adjusted R square. So instead of the equation that contains 15 terms like x1 plus x2 plus x3 plus x1, x2, x1, x3, x2, x3, x1 square, blah, 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 blah. Maybe all those terms is not needed to fit the data because it's mathematical. The more terms you put in, the better the fit it would be, okay? But using adjusted R square, you know that which term you can drop out from the equation and make it like more meaningful or making more sense, not having too complex equation to explain your data. That's how adjusted R square would be used. Okay. All right. Okay. Any question from Epic LA หรือว่าคนอื่นอยากจะถามอะไรหรือมีอะไรที่แบบไม่มั่นใจอยากจะให้อาจารย์อธิบายเพิ่มบ้างไหมคะหรือว่าเรารู้ไหมคะว่าจริงๆแล้วรู้เรื่องพวกนี้ไปทำไมอันนี้ถามแบบตรงๆเลยนะ
อาจารย์คะ
ค่ะ
อยากให้อาจารย์อธิบายอันเมื่อกี้เป็นภาษาไทยอีกรอบได้ไหมคะ
อันเมื่อกี้คือเรื่อง adjusted R square ใช่ไหมคะ Okay. Epically, I will have to speak in Thai because your friend wants me to repeat that thing again in Thai. Okay, so for you, for Epically, if you have more question on that, you can ask later when I finish explaining in Thai. คืออย่างนี้ค่ะ ในการปกติเนี่ยเวลามันมีเรื่อง R square หรือเรื่องอะไรพวกนี้มาเนี่ยมันเป็นเรื่องของการที่เราต้องการหาสมการเพื่อที่จะเอาไปฟิตหรือจะเอาไปอธิบายค่าที่เราได้จากการทดลองนึกออกไหมคะทีนี้เนี่ยอย่างที่อาจารย์บอกก็คือว่า ส่วนมากเนี่ยเวลาทำสมการพวกนี้มันก็จะมีค่า r square มาให้เนาะแต่อย่างน้อยอาจารย์อยากจะให้เรารู้ว่าค่า r square นั้นเนี่ยค่าสูงค่าต่ำก็ไม่ได้หมายความว่าจริงๆแล้วการฟิตมันแย่นะคือมันไม่จำเป็นที่จะต้องเป็น r square เท่ากับ 0.99 ถึงจะบอกว่าสมการนั้นฟิตดีเพราะว่าสุดท้ายแล้วเนี่ยค่า r square ด้วยตัวสมการหรือด้วยตัวสูตรที่ใช้คำนวณ r square จริงๆเนี่ยมันใช้กับ linear regression เพราะว่าใน linear regression เนาะ y เท่า mx บวก c นั่นแหละค่ะ sum of square total sum of square เนี้ยมันจะเท่ากับ sum of square error บวก sum of square ของ regression หรือว่า sum of square ของไอ้ residual error อ่ะไม่ใช่ที่เป็นสูตรนั้นนะคะสูตรแรกนะคะแต่ใน non-linear model เนี้ย sum of square total จะไม่เท่ากับ2เทอมนี้บวกกันนั่นคือทำไมอาจารย์ถึงบอกว่าถ้าเกิดจะใช้โอ้เดี๋ยวนะทำไมของอาจารย์หายไปเดี๋ยวอาจารย์เอ่อโอ้โอรอนเอ่อเพราะฉะนั้นก็คือว่าถ้าสมมุติว่าเอ่อถ้าสมมุติว่ามาดูตรงนี้นะคะอันนี้เราเห็นหน้าอาจารย์อยู่เนาะแป๊บนึงค่ะขอแชร์ไม่ได้แฮะเดี๋ยวอาจารย์ดูจากตรงนี้ก็ได้ค่ะพอดีหน้าจออาจารย์อยู่ๆก็หายไปนะคะแต่เดี๋ยวอาจารย์ดูจากสกรีนอีกอันหนึ่งโอเคนั่นคือหมายความว่าไอ้ตัวนั่นหมายความว่าขอโทษนะคะผิดพลาดทางเทคนิคอย่างรุนแรงก็คือในอันนี้เนี่ยเราก็คือจะเห็นว่าใน non-linear model เนี้ยใน non-linear model เนี้ย SS total มันจะไม่เท่ากับ2ตัวนี้บวกกันแต่ใน linear model 2ตัวนี้เนี่ยเท่ากันนั่นหมายความว่าถ้าสมมุติว่าเรากลับไปดูที่สูตรการคำนวณ r square นะคะดูที่สูตรคำนวณ r square เนี้ยของ non-linear regression เนี้ยสูตรคำนวณพวกนี้มันจะต่างกันไปนะคะถ้าจำไม่ผิดสูตรไอ้พวกนี้มันจะต่างกันไปเพราะฉะนั้นก็คือ r square ของ non-linear regression เนี้ยมันจะออกมาไม่เหมือนกับ linear regression ทีนี้เนี่ยพอมาเป็นนั่นหมายความว่าถึงเวลาเราทำ multiple regression หรืออะไรก็แล้วแต่ที่เวลาเราจะ predict ไอ้ค่าจากการทดลองเราเนาะโปรแกรมเนี่ยมันมักจะคำนวณมาให้ทั้ง r square แล้วก็ r square adjusted ก็จะมีค่าแล้วมันก็จะต่างกันอยู่ค่าหนึ่งเพราะฉะนั้นเวลาบอกว่า r square ของ non-linear regression เนี่ยค่ามันอาจจะไม่ใช่ 0.99 หรืออะไรแต่มันก็คืออาจจะฟิตดีได้ระดับหนึ่งเพราะว่าเราก็จะเห็นว่าเวลาทำ verification experiment เนี่ยค่ามันได้ใกล้เคียงกับค่า predict ในลักษณะนั้นเป็นต้นนะคะเพราะฉะนั้นถึงแม้ r square จะไม่ได้เยอะมากเนาะอาจจะเป็นแบบ 0.96 หรือ 0.93 นะคะแต่ก็ไม่ได้หมายความว่ามันฟิตไม่ดีนะคะ based on ที่บอกว่าค่า r square เนี้ยมัน work จริงๆเนี่ยสำหรับ linear regression เท่านั้นแต่สิ่งที่มันให้มาคือ r square กับ adjusted r square ซึ่ง adjusted r square เนี้ยเนื่องจากว่ามันจะเป็นตัวที่บอกว่าไอ้โมเดลอะค่ะสมการที่เราใช้เพื่อที่จะ predict ค่าจากการpredict ค่าเนี้ยมันมีเทอมเยอะเกินไปหรือเปล่าเทอมที่ว่านี้หมายความว่าสมการเรา complex หรือว่ามีอะไรหลายๆตัวบวกกันเยอะมากเกินไปหรือเปล่าประเด็นก็คือว่าเนื่องจากว่า
การ predict ค่าพวกนี้มันมาจากสมการทางคณิตศาสตร์ถ้าคุณยิ่งเพิ่มเทอมเข้าไปในสมการเพิ่มเข้าไปมันก็จะฟิตดีขึ้นนึกออกไหมคะแต่นั่นก็ไม่ได้หมายความว่ามันเป็นเรื่องที่ดีเพราะว่าสุดท้ายแล้วเราไม่ได้ต้องการสมการที่มันคอมเพล็กซ์แล้วก็มันไม่มีนิ่งฟูอะไรแล้วก็ไม่เป็นอะไรพวกนี้ด้วยนะคะเพราะฉะนั้นเนี่ย adjusted R-square เนี้ยมันมีเอาไว้ดูในกรณีนี้ก็คือสมมุติว่าคุณมีสมการอันนี้แล้วคุณมีความรู้สึกว่ามันมีบางเทอมที่เอาออกก็ได้ไม่เป็นไรมันไม่ได้ไปเอฟเฟกต์กับค่า y ที่คุณจะได้ที่มันจะ predict ออกมาสมมุติว่าคุณเอาเทอมนี้ drop ออกไปแล้วคุณคำนวณ adjusted R-square R-square คุณไม่เปลี่ยนหรือเปลี่ยนน้อยมากอย่างเงี้ยอาจจะเปลี่ยนไป 0.01 แสดงว่าจริงๆแล้วเทอมนั้นในสมการคุณสามารถเอาออกได้เลยมันไม่ได้มีผลอะไรกับการ predict ค่าเลยแต่ถ้าเทอมที่คุณเอาออกไปปุ๊บ adjusted R-square เปลี่ยนไปเยอะมากนะซึ่งยังไงมันต้องน้อยกว่า R-square อยู่แล้วความต่างมันเปลี่ยนไปเยอะมากเนี่ยก็แสดงว่าเทอมนั้นจริงๆแล้วยังต้องการซึ่งพวกนี้จริงๆแล้วมันดูได้จากพวก ANOVA table ด้วยนะเพราะว่าเวลาคุณทำ modeling คุณทำ RSM เนี่ยมันจะมี ANOVA table ออกมาซึ่ง ANOVA table นั้นน่ะมันเป็นการที่บอกว่าแต่ละเทอมที่อยู่หน้าซ้ายมือเนี่ยอะไรเอฟเฟกต์หรือไม่เอฟเฟกต์กับค่าโมเดลอะไรแบบนี้ค่ะเพราะฉะนั้น adjusted R-square เอาไว้ดูตรงนั้นด้วยนะคะอันนี้ก็เป็นเป็นส่วนหนึ่งนะคะเป็นส่วนหนึ่งที่ใช้ประโยชน์เนาะ
อาจารย์ขอบคุณมากค่ะ
โอเคค่ะโอเคก็ถ้ายังไงก็คือก็น่าจะเป็นเท่านี้นะคะสำหรับเลคเชอร์วันนี้ so I think that's all for the lecture for today and next week when we see each other we start the inferential statistics okay and what I want to tell you is that in the last lecture okay in the last lecture I'll take any question that involve in your research and the use of statistics if I could answer or explain a little bit more to you about those don't hesitate to bring those questions to class okay all right so that's it for today and I'll see you next week then you can leave the room thank you very much everyoneช่วยเอ็นได้ไหมช่วยเอ็นนิดนึงลีฟเดี๋ยวนะเพราะว่าของนอยพอมันเป็นแบบนี้มันไม่รู้จะทำOkay. You can leave the room, okay? Because I'm going to end. I'm going to end this room now. Okay. Thank you, everyone.
ขอบคุณครับอาจารย์
ขอบคุณค่ะอาจารย์